Okay, so here's theorem 2. And so theorem 2 talks about the associative property and distributive property for matrices. So it says if F, G, and H are matrices and the matrix products are defined, then the product is associative, meaning we can multiply it this way or in this way and they will be equal. Okay, notice that we're changing the groupings of which matrices we are multiplying, but not the order. Okay. Also, it also distributes over matrix addition. So, for example, if I'm multiplying this sum on the left, then it would be equal to the multiplication, the sum of the products with F on the left. Also, if I multiply the sum on the right, it's going to equal the sum of the products with F on the right. Okay, so again, just be aware of the order. Okay, now the proof is pretty straightforward. And again, it's just, yeah, straightforward. So proof, it says associativity holds because matrix multiplication represents function composition. That's the key thing. Function composition, which is associative. So the maps of F circle G circle H, where you're doing this side first, and F circle G circle H, where you're going to do this grouping first, both send the vector V to the same place. It's still going to go through this process. Okay? F of G of H of the vector V. Okay? So now distributivity is similar because, for instance, if we take the composition of F and the addition of these two vectors, so F circle the sum of G plus H, that's going to be equal to, by definition of a composition, F of the sum G plus H of the function. And then, of course, as we've seen before, we can distribute this across the addition of functions. So that gives us F of G of V plus H of V. And of course, we now can break this apart, and this is F of G of V plus F of H of V, which is the same thing by definition of composition. F circle G of V plus F circle H of V. And doing the right side is a similar argument. And that proves the result.